using strictly pixels, which means for every spot on the screen, we draw something. And that's fine when we're working with a small amount of pixels. I'm going to go real quick over to the One Lone Coder Javid X9 repository, where we will find, actually, a moment. Let me go over to Joseph21's repo, containing a Pixel Game Engine version of the Retro Arcade Racing game. And we'll start with that one and go, start with that one and go from there. The reason why I want to show this is to just demonstrate the core issue here. This is just a re-implementation of what the console game engine versions of the Pixel Game Engine racing game looks like. And this is fine. It works great. You can see our FPS actually already dips pretty low. And the reason for that is because every single thing you see on the lower half of the screen is rendered pixel by pixel. Actually, same with the hills as well. So, and this was required because the console game engine, every single character ran on pixels. This becomes even more exaggerated when you try to do what Rune wants and make a version of the game in 720p. Everything scales based on the width and height of the viewport. So we can see here, well, the game looks fine, but oh man, the FPS has taken a hit. And the reason is because we are drawing hundreds of thousands of pixels at once instead of just, before it was maybe a couple 10,000s. Now we're drawing we're iterating through over 400,000 pixels every single frame. And this is unacceptable for a game. We would like to build our game better, and it's not like it's a very crazy complex game. Why is it lagging? Well, the reason why it's lagging is because we're iterating through so many pixels and doing so many things at the same time. Luckily, the Pixel Game Engine has the ability to do hardware rendering using the decal system, and hardware rendering is going to be our solution to optimize the racing game. Over the last few days, I've been helping Rune do said thing, where we've been converting every single element of this racing game to hardware rendering using decals. So if I back up to what I have here right now, this is going to be the final product of what I'm demonstrating today. I'm basically going to be explaining how the racetrack generating code, the part that makes a curve, works. Here's just an example. I just have some random sprites on my computer for various things. But this is what it looks like, and you can see it is running at 720p and with over a healthy 200 FPS, and it looks pretty much like what the original does, actually a little less pixelated because it's doing hardware rendering. And we can see it works great, it works smoothly. This is what we would expect from a game like this. But how is this done? Well, that's what we're going to cover. I've already helped Rune do the mountain, the skybox, and the grass rendering, as you can see. Those are all fine. So we're going to talk about the track, which is rather interesting, because the track curves, and the curve is dependent on a mathematical formula based on perspective, which came from the original video that Javid did for his tutorial series. I'm going to start from this file, which is where I left off with Rune, I think yesterday. So this is roughly where we're going to start. I'm going to delete this. Okay, let's just have a look at what it looks like right now. I've taken the time to change all the resources to use my stuff, and we can see there's currently no track. The track is actually beneath these. These are all decals. You can see it's running at like a 16 FPS right now. Due to all the rendering code of the track, it's just invisible. If I hide the grass real quick, we can just see that the track is indeed there, but it's using the old rendering code, and that's why it's so laggy. So there's mountains here too. I think I uncommented the wrong mountain code, but you can see it's really laggy. The track is indeed there. It's just not what we want, of course. Anyway. So we're gonna fix that. Firstly, I'm going to get rid of all the grass code, because there is grass now. And so we're just gonna get rid of this, get rid of this. When it says left clipboard and right clipboard, those are the curbs of the road, the red and white parts. And then the road itself is, of course, the road itself. For now, I'm actually gonna get rid of everything, so we can just take a look at what the rendering speed is right now. Also, you can see my grass is kind of... So you can see it's like 28 FPS right now. So why is it still slow? We took out all the rendering code, and I even claimed that it's because we're drawing so many pixels on the screen. Well, that's not the whole story. Also, my grass is kind of... So my grass is a different size, so I can't use the same dimensions here, so I just changed it. It's actually a 2 pixel tall image window, so this looks a little bit better now. So yeah, what's up with this 26 FPS? Upon further investigation, I noticed that all this code is running inside of 2 for loops. And that's kind of concerning, because in the original code, I wish I didn't just straight up deleted it, but we'll go back real quick. There we go. So here's the original code. There we go. And I realized that the perspective is only based on the Y position. So that means all these calculations are currently happening for every pixel on the screen every single frame. This was less of a problem when we had less pixels on the screen, but now, oops. Now that we have more pixels on the screen, it's time to optimize. So this outer for loop that iterates across all the X positions on the screen can actually be moved into here. And we'll have to do some little code reorganizing here. Putting the Y loop as the outer loop instead, which doesn't affect anything internally. It just means when it's time to draw, that's where we iterate through the X. And this is just a minor optimization. We're actually going to replace all that stuff. But you can already see the FPS has gone up quite a bit to 42, because now all we're doing with the iteration stuff is drawing what's on screen. All these calculations, they're all only based on the Y position, so we don't need the X for that. So we just removed tens of thousands of calculations, just like that. It's a minor optimization. In the end, we're replacing all of this anyways. It's just something to note. So let's talk a little bit about the theory of what I came up with to make this curvy track thing that is currently being rendered using individual pixels. The Pixel game engine has a very powerful function. It's called Draw Polygon Decal, and it will draw an arbitrary convex textured polygon using the GPU. I was thinking to myself, how can we render a curve? And the easiest way to do that is to specify all the points along a curve and render it as a polygon. And luckily, the Pixel game engine supports such a feature, and it'll be done using hardware rendering, which is fantastic. There are a couple of arguments to draw a polygon on screen. It first needs a decal. This is the texture. We essentially need to think of this in terms of 3 dimensions, like a 3-dimensional object, which is just 2 dimensions on screen being translated. And you'll see what I mean in a second. It needs a position, which is a vector of vectors. Yes, floating vectors. Pixel game engine vectors. And then we need a vector of more vectors, which is UV. So you might be thinking, wait, UV? UV mapping is usually used for texture mapping in 3D games. So yes, we're basically drawing something using 3D to 2D texture mapping concepts. And finally, we can tell it what colors each particular point on the polygon is supposed to be colored, or we can use a default of white, which is what we're going to do here. We're not going to tint it at all. So we're going to render a polygon of some sort. That's what we know. So how are we actually going to accomplish this? I'm going to go over to here real quick. Oh, my drawing tablet. Okay. So right now, my bad. Okay. Let's just get a screen up real quick. That is not a screen. That is a line. So this is our game screen, and right now, the bottom half is being used to draw, say, a road. Normally, when the road is straight, it looks something like this. It's got some perspective to it. I do not want to snap to a grid, thanks, computer. My other line looks nice, though. And then when it's time for the road to turn, it starts doing something more like this. Or maybe the other way, too. Either way, each of these points on the curve is represented using the current formula that was provided in the tutorial series. So that's all well and good. We already know the points along this curve. All we have to do is stuff it into a vector and then render that polygon itself. And essentially, we can choose either side, but we're basically going to connect all of the dots. Like, connect all the dots using the left side, and then connect it to the bottommost right dot, and then connect all the dots on the right side. And that will give us a filled-in polygon, which will then be rendered on the screen for us. And this works for the left side as well, same concept. And if it was just in the middle of the screen, like this, same idea. Iterate through all the points on the left. Eventually, we run out of those points. Then we connect the bottommost left point to the bottommost right point. Iterate through all the points going back up. And there's our filled polygon, like so. So that's how that's going to work. Now we just have to figure out how to do it in code. The first thing I'm going to do is create 2 vector variables that are going to hold the floating point vectors. One of these is going to hold all the positions, and one of these is going to hold all the UV mappings. And we'll worry about the UV mapping part later. For now, I'm not actually going to include the texture. This is actually what the road texture looks like, by the way, which we're going to apply to it eventually. But for now, we're just going to draw it as a flat color so that we can get things going. To make sure that we already have the correct values we need, these were appropriately named left curve and right curve. Let's just render these on the screen and make sure they're doing what we think they're doing. I'm going to iterate, or it's not iterate, I'm going to use fill circle. And I'm just going to draw a green circles on the left side curve and red circles on the right curve, so we can make sure that these are the values we want to use. This is just more along the lines to show what's happening. For the Y position, we actually iterate through the top half of the screen. This just makes calculations easier. We iterate from 0 to half the screen height, and then later, this row value determines where the final position of the pixel is going to be, where it gets rendered. So I'm actually going to use the row variable here. And we need a radius. I'm going to make them pretty large so we can see them well. And I'm going to use the green color for the left-hand side. And the red color for the right-hand side. And this is just going to iterate through every position in the y-axis. I also need to get rid of some other stuff so we can focus on just the curve. So I'm going to disable all the other fancy graphics we have on screen right now. That's all well and good. We're not worried about that. And actually it reveals the underlying drawing, which we're going to disable now because we know for sure we're going to redo all that stuff. So we're left with some red and green circles. There's a whole bunch of them. They're just all drawn right next to each other, so they look contiguous. If I just start driving forward, these will eventually curve. So you can see these are the values we want to use, every single one of these points. Excellent. So knowing that, we can now focus on actually stuffing these positions into a vector. So normally, when you're defining a polygon, we're gonna go back to the drawing board real quick. You need to render things using triangles, and OpenGL uses triangles. Internally, the Pixel game engine starts by using what's called a triangle fan. If you try to draw a polygon decal, let's say you're trying to draw a box. So here's my box. And we can divide the box into a couple of triangles, kind of like this. So when it comes to triangle fanning, you specify one point, and then all other points you specify are going to be connected to that one point. So in our case, we would specify a triangle point here, triangle point here, which would be connected like this, and so on and so forth. And each time you specify one, it will automatically fill in the other one. This is called triangle fanning. You just specify at least 2 points, and it provides a triangle in between them. However, that's not going to work for our case, because we have a track where we're iterating from the Y position, the top of the screen, going downwards. And so when we're inserting these positions into our vector, we're going to want something like this, and like this, and then our next points might be like here and here. So if we did triangle fanning, and we just like kept going and picking points over and over, eventually when we get down here, we're going to have connections across the entire polygon like this. That's what a triangle fan would do. It would connect all of these points to that one point way in the corner, which is not what we want at all. So instead, what we're looking for is something like every time we specify a point, it connects those together. And then when we specify the next point, we get our nice triangle. And then if we specify another point, it makes another triangle like this. So for every additional point we add, it creates another triangle. And there is a name for this. This is called a triangle strip. So we want to use this technique instead to eventually form our entire polygon of triangles, making up the entire road. So the Pixel game engine supports a way to control how we render things with decals. We use a function called setDecalStructure, and it requires an OLC decal structure enum, and we can choose between fan, line, list, and strip. And like I mentioned before, for our technique, we're going to need the strip functionality. Fan is the default, so I just like to set it back to the default when I'm done working with it. But essentially, our vector is going to be filled up, or our polygon is going to be drawn using this technique. This actually should not be in the for loop. We're just going to render all the positions afterwards. So that was in the wrong spot, actually. It should be outside of the for loop after we're all done calculating the positions. So we're going to do pause pushback and specify our positions to add to the track. Now that we know we can just specify left, right, left, right, left, right over and over, well, let's do that. So pushback allows us to add something to a vector. We're going to first add the position located at left curb, comma, row. And then we'll add another position using the right curb, comma, row. We can also specify our UVs. Right now, they're not optional, but we don't quite know what to do with them right now, so we're just going to specify 0, 0, and 1, 1. We'll worry about those in a little bit. Now that we have our positions and our UV coordinates vectors populated, the next thing to do is to actually create the draw polygon decal function in between our set decal structure calls. That way we're doing a triangle strip and not a triangle fan. For the decal, I am using, I'm actually going to use null pointer. One of the features is that if you specify null pointer for the decal, it will just draw a flat shaded object, which is all we're going to worry about for now. The position vector is just called pause, and the UV is called UV. So it's happy with that. It's using the one where all the tints are white. So let's just build it and take a look. Okay, so right away, we can see that this is indeed the correct way to draw the polygon. If I just drive forward a little bit. Perfect. That's exactly what we're looking for. And all we're doing is we're specifying every single point from the top of the screen down and checking to see what position it matches with the formula. And then we're adding all these like triangles to create this thing. Very good. So now let's talk about the texture coordinates, because that part is pretty important. Right now I just made it so we specify from 0, 0 to 1, 1. The way UV mapping works is every position on a texture is mapped between 0 to 1. So along the x-axis, the upper left corner would be 0, 0. The lower right corner would be 1, 1. So we have to render this piece of road onto the entire section of the track. So even when it curves, the texture is curving with it. And it's kind of weird to think about at first. We can do a quick little sketch of what that might look like. Since our road texture, yeah, this is just a rough idea of what our road texture looks like. But yeah, since our road texture needs to be just plotted against the entire thing, let's say this is the rendering of our road here, and we now know it's a polygon with a bunch of triangles going side to side. Let's just imagine one of these triangles. I'm gonna blow it up so we can see it better. One of our triangles looks like this. So ideally, we want to take the texture and say, okay, render that piece of texture onto this thing. So it would kind of look like, I'm trying to use the same colors so we can kind of match what we're seeing here. It would kind of look like a bit of purple there. Got the white here. We got the white barely or visible there. Kind of look like that. And so for every triangle we add, the left sides will always use the left side coordinates of the texture here. So we know that part's pretty easy. It's going to be somewhere between 0 and the y is going to be anything from 0 to 1. We're not quite sure about the y yet. We'll talk about that in a bit. And that means the right-hand side has to be at least 1 for the x coordinate and something in the y coordinate. We don't quite know yet, but this makes it very easy. We just use x0 for UV mapping and x1 for the right side. It's very easy since we've already done it left to right. If we did right to left, we would have to invert it. So this actually almost works the way we would expect. Say almost. So I'm actually just going to replace the null pointer here with road, the decal I used for road.png. It looks like it doesn't like it yet, so I'm going to go over and take a look why. I probably just didn't create it, because it didn't exist before. And if it doesn't exist, I'll just make it real quick. Cool, it doesn't exist. Let's say initialize road image. And we do want clamping turned off for this decal because we do want it to tile, just like our other tileable decals. So you can see it almost looks like what we want, except we got one side all red and one side all white. And the reason for that is pretty simple. If we just draw, we just tell it to draw everything on the left side from texture coordinate 0, 0, everything on the right side texture coordinate 1, 1. Is this my road? Nope. I kind of wanted to show a dynamic road thing. Pull that up real quick. So if we just say always draw from here to here, then we're gonna end up with the bottom corner always being connected to every triangle on the right-hand side, while the top left corner connected to every triangle on the left-hand side. It's just going to repeat over and over. And if you look very, very closely, you can see that there was this like little white line thing here. And on the white side, you see there's a nice little white thing here. And you can actually see this when we run it. Because we're checking every single pixel, and every single triangle being rendered is just the top and bottom left corners, you can actually see this like white stripe along it. It's literally sampling just the corner spots of the textures, which is not quite what we want. So we're almost there. We got a texture on the screen, we got a road, it curves, the FPS is great, almost done. We just have to worry about the texturing now. So, in order to get this to work, we're going to be using a similar function, which I've just left here in the open, to determine whether or not it needs to be red or white. And to really visualize this, I like using Desmos. I plugged in the original formula here. This is sine of 80 multiplied by the power of 1 minus perspective, which we're calling x squared plus d. And most of this doesn't really make sense right now. But if I were to drag the slider, the effect we're getting, and we're mostly looking at this center area here with the 1, is that as the curves approach 1, they suddenly change in amplitude very, very quickly. And this is us simulating like how the curves are represented if we were to look at it. If we flipped this sideways, like 90 degrees sideways, we'd basically be seeing the frequency of each curve along the track. So we kind of want to do this. However, UV mapping is done between the range of 0 to 1. So we kind of need to clamp this value between 0 and 1. And to do that, it's pretty easy. First, we would shift the entire thing up by 1, so I would subtract or add 1 here. And now everything's above here, but now it goes from 0 to 2. So then I would divide the whole thing by 2. And now it's only half the size, so I need to bring it down to only half. And suddenly our values are between 0 and 1. And that's what we want. We want an oscillating effect between 0 and 1 in order to get us the proper result. So let's implement this. I'm just gonna... That is not the right window. So this is the exact same thing we just saw there. And so I'm gonna first copy that. Well, this was the original. We're gonna change it a little bit. D was the distance, by the way. So as we traveled along, it went on. So I'm gonna plug in this for both UV coordinates. And what we're gonna do is, after it's calculated, we're going to divide by 2 and add 0.5. I believe were the transformations we made to it. Let's just have a look. Well, it looks pretty good. Can't really complain at this point, huh? Yeah, that looks fantastic. When it was originally implemented in the tutorial, whenever the curve was above the 0 axis, the 0 x-axis, it would produce a red color. And if it was below, it would produce a white color. So we're basically taking the same concept, but now we're applying to this UV mapping, where the texture has one half being red and one half being white. But because it's in a range from 0 to 1, we had to shift that curve up. So essentially, when it's producing these, it's going wee up and down to figure out where to sample it. So that about does it. We just need to enable all the other stuff now. So I'm going to put back the grass, the mountains, and the skybox. The grass doesn't move yet with the distance. Well, we can fix that pretty easily. It's just a side effect of not finishing it from earlier. So because the grass is getting clamped, we just have to offset it based on how far we've traveled. So we'll use distance here. I think it has to be negative because as we go further, we're sampling downward, so it would scroll upward. Oh boy, that is way too fast though. We'll just divide it by like, I don't know, let's choose a nice number like 12. Much better. And there we have it. Every single thing about the arcade retro car engine is now completely revamped with decals. It's running at a smooth 240 FPS for me. Very lovely. Very good. Now we're ready to do more fun things with the game, I think. I'm excited.